Hey, this is Tony from Adafruit, and in this video we're going to look at how to use the LIS3DH accelerometer with CircuitPython. So an accelerometer is a little sensor that can measure acceleration, and there's all kinds of acceleration around you. So things like, if you're moving, if you move your arm, or if you're in a car or something that's moving, or the force of gravity, which is constant acceleration, 9.8 meters per second squared, going down towards the center of the Earth. And so it's really handy. You can do a couple things with it. You can detect motion, like if you're moving something around or if you're twirling something, or you can detect orientation because you usually have multiple axes of acceleration, like an X, a Y, and a Z axis. And so you can tell how those axes are oriented for a stationary object compared to gravity. So you can see, if one axis is facing down, then your device is in a certain orientation. So really handy little sensors that you can use to detect motion and orientation. And the LIS3DH is a really nice little inexpensive sensor. I think it's only $5 in a breakout, so very, very inexpensive, easy to add to a project, and you can add cool interactivity like orientation and motion sensing. Even has some extra features too, like a tap or a click detection on it that we'll look at. And in this video, we're going to see how to use this with CircuitPython. So remember, CircuitPython is Adafruit's version of MicroPython that's a little more beginner focused. And so we'll look at a little library or a module that I created that lets you access the accelerometer and all of the readings from it in CircuitPython. And one little note, this does currently only work with CircuitPython. In the future, we're going to look at some different wrappers that'll let this work with MicroPython. It's really just a minor difference in some of the SPI and the I2C APIs. So probably in the future, there'll be some shims that you can use to use this with MicroPython. But for now, just be aware, you do need to use CircuitPython with this. So we'll kind of dive in and we'll get started. And we'll look at, there's actually a guide that I wrote that we'll follow along with for this project. So let's switch to the main view and we'll see. This is the guide that we'll walk through, and it's not published just yet, but by the time this video goes up on YouTube, I'll make sure that this is published and that people can see it. So we'll walk through this guide. I'll kind of show you how to wire up the sensor to your board and then how to install the CircuitPython module and use it. We'll use it from the REPL and maybe even run some of the example code that's included in the library for it. So let's see, let's kind of get started here. And the first thing is in the guide just talks about what the accelerometer is. Like I mentioned, it measures an acceleration force, which you can do a couple things with. You can detect motion or you can detect gravity. So like which way something is facing. And this accelerometer in the upper right hand corner here, this is the two pieces of hardware that I'm going to use for this video. So right here is the LIS3DH breakout board. So that's the accelerometer in the middle right there. And then little breakout just makes it easier to connect to it. Does things like convert the voltage between like 3 volts and 5 volts, has a little power regulator on it. Makes it really easy to use this chip. And then right here, this is the Feather M0. This is the Adalogger version, so it has SD card. You can use any CircuitPython compatible board for this though. So the ESP8266 or the Feather M0 boards, even just the basic M0 would work. And you can wire this up to the LIS3DH. Nice thing about this chip, it supports either an I2C or a SPI serial interface. So you can use whatever's most convenient. I would recommend the I2C interface. That's how I've wired it up right here. I show in the guide how to use either interface, but I2C is simpler. It uses a few less lines. You just need a clock and a data line and then the power and the ground lines. So really easy to use, and you can have multiple devices sharing the same I2C bus. So for small devices like this, like sensors, when you don't really care about this crazy refresh rates and speeds, it's a little bit easier with I2C, I think, to get started. So that's what I would recommend for this. So let's see, we'll dive in here and get started and look at this guide. So the first page in the guide talks about the hardware. So like I said, what you'll need to follow this guide, you'll need a board that runs CircuitPython. And like I said, you do want to use CircuitPython. So right now, this library doesn't work with MicroPython. It's a minor API difference. In the future, there'll probably be a shim layer where you'll be able to use this library with MicroPython. But just for now, we're still kind of creating a lot of these things. And so, like I said, you can use this with the ESP8266 or a SAMD21 board. And the SAMD21 boards usually have M0 in the name, so like the Arduino M0 or the Feather M0 boards. Or the ESP8266, super popular Wi-Fi microcontroller. Either of these run CircuitPython, but you do want to load the CircuitPython firmware. I have a link to some of the guides that mention how to do this, so make sure to load the latest version of the firmware on here. And then, of course, you'll need the LIS3DH accelerometer. So this is a link. And by the way, I'll put links in the description when this is up on YouTube down below, so you can see a link to this guide that we're looking at, product page, and any other pages that I look at here. But this is the board, like I mentioned, a really nice little accelerometer, very inexpensive, like $5. You know, who can believe, like 2017, it's pretty amazing what you can get with technology these days. For $5, you get this tiny little chip that can detect gravity. Like, it just blows my mind. You know, look at how small that little thing is. It's pretty amazing. I think, was it Louis C.K. had the kind of classic joke of like, you know, imagine you're flying in a plane, you're in a tube that's in the air, and you know, and you're complaining about something. So it's amazing what technology can do for us these days. And these sensors are pretty fascinating from what I understand. They're built with MEMS, the microelectronic machinery, I believe. So from what I'm not an expert on this, but I believe inside of here, they're basically these tiny little springs and balls that detect the forces, because really the force of gravity or acceleration is just movement. And so if you have a spring and like a known weight on it, and you can detect how far that spring moves or how much it deflects, you can infer how much force is applied to something. And this has 3 axes, so triple axis, which just means there's, you know, a z-axis that goes up and down. There's an x-axis that maybe goes left and right, and a y-axis that goes in kind of the opposite direction there. So there are 3 axes, which that gives you a way to understand kind of 3 dimensions of movement. So there are 3 of those little springs and ball contraptions inside of this tiny little microchip. I believe that that's like created directly in the silicone. I mean, these are fascinating devices. It would be really cool to do more of a deep dive and see what's inside of one of these chips. But really cool that that's what you can get. You know, for a few dollars these days, you can get this space age technology. If you had this chip in the 1960s, you would have blown all the scientists' minds. This would have been, you know, this amazing technology, and now everyone has it. And the reason why these are so inexpensive and easy to get is because every single cell phone, I don't have mine on me, surprisingly, but if you have your cell phone, every single cell phone has one of these chips in it, almost every single cell phone, unless you have a really low-end one or an old cell phone. Because these are the chips that tell your cell phone if you're holding it in portrait or landscape orientation, because it's just detecting that force of gravity. So this is the cool thing. You can do that same kind of detection in your own project using an accelerometer. Anyways, though, so back to the guide. You'll obviously need the LIS3DH, and then you'll probably want a breadboard, some hookup wires, and you'll need some soldering tools, because like any breakout, you have to solder on the strip of headers to this. Really easy soldering. So if you're a beginner, check out the guide to excellent soldering. Just do a little bit of practicing. It's very easy to solder headers onto things. Great beginner soldering thing. So don't be intimidated by that. Like I mentioned, so before you get started, though, actually follow the LIS3DH guide. Actually, I'll open this up so I remember to put a link in the YouTube description. So this is the guide for this product. You know, like all products, when you buy the product, follow the guide. It tells you any gotchas, what you need to do to assemble it, which is literally just solder on this strip of headers right here, and you're good to go with it. But it tells you a little bit about it, like what all of the pins mean on here and things like that. So you do want to check that out. And then for wiring, so like I said, there are 2 ways that you can wire this to your board. So you can use I2C, or you can use the SPI protocol. And there's really no advantage or disadvantage to either. They're just trade-offs. So I2C requires less pins, whereas the SPI interface requires a few extra lines. There's a chip select line, and you need an output and an input line for this. Like I said, I think the I2C interface is the easiest for this board, so that's what I would recommend for wiring this up to your board. And that's how I have mine wired right here. So just like this diagram shows, I have this green wire right here, and my wire colors are different, sorry. But this green wire, the white wire right here is my voltage input line. And I actually have mine connected to the USB, which is the 5-volt output of the Feather board. But in the diagram here, I have it connected to 3 volts. You can use either. That's the nice thing about this breakout board. It can be powered off of 5 volts or 3 volts. So whatever power source you have, you're fine. As long as it's within like 0 to 5 volt. Well, you need more than 0 volts. So within like 3.3 volts to 5 volts or so. Check the product page and the guide. It'll tell you exactly the range for it. Anyways, the green wire, this is going to the ground connection, so it's just the ground connection to my board and then to the LIS3DH. And then the orange wire right here, this is going to the SCL, or the I2C clock line. And then the yellow line is the SDA, or the I2C data line. And so just follow this diagram and you'll be all set up to connect this to your board. Or if you use the SPI protocol, just be aware that you need an extra data line for a chip select. That's the blue line right here. And that needs to be connected to any of the digital inputs or outputs on your board. So as long as it's a digital input or output that you can control, then you're good. But just be aware that you do need to use that. And if you use one that's different from what this diagram shows, I'm using pin number 6, digital pin number 6. You'll need to change the example code to use the appropriate pin number that you've selected for this. So just be aware that things might change depending on how you wire this up. Okay, so that's it. Once it's wired up, we're pretty much ready to go and use the software for this. And it's pretty straightforward to use this. We basically just need to copy a couple modules onto the board's file system. That's the really cool thing about MicroPython and CircuitPython. It has a little file system on the board. You copy your modules onto that file system, and then you can start interactively using them. So, you know, it's unlike in the Arduino world where you have to install libraries and compile code. You just copy these libraries right onto your board and you're ready to go. So I talk about in the guide here, the very first thing, make sure you're running Adafruit CircuitPython, and I have some links here to more of the information. And then we're going to use the module, which is on GitHub right here. So this is the module itself. And if you follow the guide, basically you want to go to the releases page right here. So I'll open this up. And on the releases page, look for the latest release, and you'll see a zip file, and you want to download this zip file. And then we want to copy the contents of that zip file. You'll see a folder inside of there. You want to copy the contents of that to your board. And there are a couple ways to do that. I mentioned right here, if your board supports a USB mass storage mode, like this M0 board, then you can just drag and drop copy it. Unless you're on Mac OS X, in which case I mentioned you have to do this workaround because it creates these hidden files for things that are downloaded from the internet. So just FYI, and I have a link here to a guide page that tells you how to work around that. If your board doesn't support USB mass storage, if it's like an ESP8266, you can use a tool like Ampy, and I have some links to the guides right here. That's a little tool that lets you copy files and run scripts on a MicroPython or a CircuitPython board. So use the appropriate tool to copy these directories onto your board. Now be aware, for this module, it does require one dependency. It needs this Adafruit CircuitPython bus device module to also be installed. So I'll show you how to install both these modules on this M0 board. So basically, I will drag over the Finder right here. And I've already got right now the bus device zip file, which I downloaded just by following the guide here. And then I opened it up, and there's this bus device folder with these files inside of it. And then this is the LIS3DH zip file. And so I'm going to extract this. And inside of here, there's a directory with some files inside of it. So what I need to do is copy both the bus device and the LIS3DH folder. So both of these folders, not the zip files, the folders need to be copied onto my MicroPython board. And so that's, you can see it shows up as a drive, or my CircuitPython board rather, shows up as a drive called CircuitPy. So I'm just going to drag these onto this board. And this should work because it's only a few files that I'm copying over. If you get an out of space error, then and you're on Mac OS X, then you're probably running into this issue right here, and you're going to have to use a manual copy command to make this work. So just be aware, it's this weird little quirk about how Mac OS X deals with files. Okay, so once you've copied these over, we're ready to start using this library. So what I'm going to do is I'm going to actually, so the guide kind of walks through, there's some example code, and the example code, you don't get it when you download that release. You have to go on the GitHub repository. So if I go back to the GitHub page, there's an examples folder, and I have links in the guide to all of these things. And so there are three examples. There's an example of using the accelerometer, the analog to digital converter, which are actually these three little pins that are available on this board. It's a very limited ADC, but you can do some limited analog to digital conversions with it. And then there's also a click or a tap detection on the board. So there's an example of how to use that. So I'll walk through how to use that real quickly. Maybe I'll do it first with the REPL, and then maybe we'll run one of the examples. And in the guide here, I walk through each of the examples and how to use it with your board. So let's just open up the serial terminal. So I'm going to connect, so my board is connected to my computer. It shows up as a serial device, and I'm going to open up that serial terminal. This is the serial REPL, if you're familiar with MicroPython and CircuitPython. So on Mac OS X, I'm going to use the screen tool, and I'm going to open the USB device for this M0 board, 115200 baud, that's the baud rate you need. And then I open this up, I press enter, and I get the Python prompt here. Okay, so now to import and use this module with CircuitPython, first I need to import the board module. This gives me access to all the pins that are on this board. And then I need to import, so because I'm using the I2C interface, and because this is an M0 board, which has a hardware I2C interface, I'm going to import the native I/O module. If you're using a software I2C interface, you would import the bitbang I/O module instead. And I mentioned in the guide, actually all of the examples at the very top, they have this same bit of code, and they show 3 ways to initialize this board. So the top is with the hardware I2C interface. The middle one here is with a software I2C interface, and the only difference is I'm just using this bitbang I/O module instead of native I/O right here. And then the third one is with a hardware SPI interface. And so this just shows there's a little bit of a difference here in that you're using that chip select pin. So like I mentioned in the guide, if you're following one of the examples, you just want to follow one of these import methods, or one of these configuration methods for initializing the hardware. So you'd either comment or uncomment the appropriate one for your hardware. Since I'm doing this with the REPL, I can basically just look and see which of these lines of code that I want to run here. So anyways, since I have a hardware I2C interface, I imported the native I/O module. I need to create that I2C bus. So that's using the native I/O module. There's an I2C class inside of there. I need to tell it what the clock and the data lines are for this board. So that's from the board module. It has the SCL, the clock pin, and then the SDA, the data pin here. So I'll do that. And oh, that's kind of interesting. It's already in use. So I must have already initialized the I2C interface. So what I'm going to do, I'm going to press Control D. D is in dog. And what that does is that just reboots the board. Because I've been testing this out earlier, so I probably already had it initialized. And so it's helpfully telling me that you've already initialized I2C. So that's what happens when you see that error. Anyways, I just reset the board. So I'm going to press Enter now to get back to the REPL. And let's just run this again. Import board, import native IO. And then let's create that I2C interface. So native IO.I2C, board.scl, board.sda. There we go. So now I've got the I2C interface. Now I'm going to import the LIS3DH module. So import Adafruit _ LIS3DH. This imports the module that we copied over. And at this point now, I need to create an instance of the LIS3DH class. And so there are actually 2 classes inside of this module. And if you use the dir command, you can see everything inside of here. So there are a bunch of constants inside of here, things like data rate and register values and things. But the 2 classes that we care about are right here. So there's LIS3DH SPY, and then there's also an LIS3DH I2C somewhere in here. Here it is. So these 2 classes are basically how you initialize the LIS3DH class. So there's a class for an I2C interface and a class for a SPY interface. And again, the example code here shows which one you want to use. Like when you're using hardware I2C, you use this I2C class, LIS3DH _ I2C. If you're using SPY, you use the LIS3DH _ SPY interface. And that's just because the class needs to know the protocol because it slightly differs in how it talks to the chip when it's using SPY or I2C. So in my case, I'm using I2C, so what I'm going to do is I'll make an LIS3DH object, and I'll set it to, in the LIS3DH module, the LIS3DH _ I2C class. Now this just takes in one parameter to its initializer, which is the I2C bus that we just created a second ago, this object right here. So I'll pass that in. And okay, at this point, I'm ready to start using this object. Now, if you get an error, like this initializer might throw an error because when it runs, it will actually check to see if it can detect the LIS3DH chip. It's actually reading a little register on the chip that says this is an LIS3DH sensor. And if it can't read that, it will throw an exception that says, hey, I can't find the LIS3DH. So if this line of code throws an error for you or an exception, it's very likely there's a problem with the wiring and it can't talk to the chip. So check your wiring, check the power to the chip, like you've got either 3 volts or 5 volts into the VN line, the ground is connected. That's a really common mistake sometimes, or maybe not mistake, or issue that causes that problem. So, try fixing up the wiring, make sure that you can actually talk to the chip, and then try it again. And if you don't see an error, then you should at least know that, okay, it was able to talk to the chip and things should be okay. Now at this point, you can start using on this LIS3DH object. If I look at it with the dir command, this will show some of the functions. Oh, unfortunately it doesn't show the functions because it uses, in the implementation of this, I use I use a base class and a subclass, and in MicroPython, the dir command doesn't actually show you what the base class functions are. So anyway, sorry, long story short, look at the guide. I talk about the functions here in the guide, and we'll start with the accelerometer. So to use the accelerometer, there are a couple interesting things. So there is a range property on the LIS3DH object. So if I just run lis3dh.range, what this does is this returns back the value of the range that's set for the accelerometer. And you can set this, it's a property, so a property you can read or write. And I can actually set this to, in the module, there are some constants defined inside of here. And so in the example code, it mentions there's like a range underscore 2G constant, range underscore 4G constant. So I can say like range underscore 2G. And this is going to set the range of the accelerometer to be plus or minus 2G. And G is just a unit of acceleration, a gravity, which is what the accelerometer kind of uses internally. So I'll set this to the 2G range. You can go 2G, 4G, 8G, or 16G of range. Now the thing is, if you go to a wider range, you still only have like 10 or 12 bits of accuracy within that range. So sure, you can read plus or minus 16 Gs of acceleration, that's a lot of acceleration, but you're only going to read that entire range with that 12 bits of accuracy. So you'll have much less accuracy. You won't be able to tell the difference between a very small change in acceleration with that 16G range. Whereas if you go down to the 2G range, you've got that full 10 or 12 bits of accuracy for that smaller range. So you can tell smaller differences in acceleration, but you can only tell acceleration that's between plus and minus 2 Gs of acceleration. So it's a trade-off. Again, nothing's perfect. It's a $5 sensor. What do you expect? So you can only detect kind of either a small range with a lot of accuracy or a wide range with much less accuracy. So you've got to kind of think for your project. If you're sensing 16 Gs of acceleration, it's a pretty serious amount of acceleration. I think humans pass out after 8 Gs of acceleration or something like that, like a fighter pilot experiences that. So, you've got some serious acceleration going on at that point. So probably the 2G range is fine, and that's, I think, what it defaults to. But this is an example of how you can set that acceleration range. But if I wanted, I could set it up to like the 16G range if I wanted like that. And now if I read the value of this, I get this value 3 back. Which maybe isn't that interesting, but in your code you could say, okay, if lis3dh.range equals your Adafruit lis3dh range underscore 16G, then maybe print out 16G, something like that, and then that runs your code, so you can test and see what your values are for that. I'm going to set it back to 2G of range just because I want to get that smaller range. Okay, now to read the acceleration, super easy. You just call LIS on that 3DH object, call the read underscore accel underscore G function. And so this is going to return back a 3 tuple. So in Python, this is the awesome thing about Python. If you want to return multiple values, you can do that with a tuple object, whereas in Arduino and C and C++, it's a little bit harder to do that. So this returns 3 values, and this is the X. The first value is the X acceleration, then the Y acceleration, and the Z axis acceleration. And the units that it returns are gravities, or Gs. So you can actually see the Z acceleration is 0.966 G, which is pretty close to 1. And that makes sense because the z-axis, if you look on the board, it's hard to see from this camera view, but it's labeled. The z-axis is the one that goes up and down, like it's actually coming towards the camera. That's the z-axis. And so that's basically telling me that, you know, it's seen 1g of acceleration down, which is good because that means it's detecting the force of gravity down towards the Earth. And now if I hold this upside down, like, you know, if I flip it over, so now the z-axis is flipped around, and if I run this again, now we see it's negative 0.96, or, you know, just about -1. So that just means that it detected, I flipped it over, and now it sees that that z-axis is in a different orientation because gravity, you know, gravity didn't change. I didn't flip the room around. I flipped the sensor around, and so it sees that gravity is coming from a different direction now. And that's how you can do kind of that basic orientation detection. And like the cool thing is, so if I hold the sensor like this, and so in this orientation, the y-axis is facing down now. So I should see this middle one have a value of around 1 when I call that readXLG function, or -1, it turns out. Sorry, it's the other way. And that's true. So I see that. So, you know, I can detect if this thing is held in this orientation. And if I flip it around the opposite way like this, I should now see like a +1 value. And that's what I see for that y-axis there. So that's pretty cool. And then the nice thing is with Python, it's got this feature called Tuple Unpacking, or Tuple Unpacking. I never remember how to pronounce that. I need to see how the Python experts pronounce it next time I'm at PyCon, which, by the way, I will be doing a small talk at PyCon, the Education Summit. So if you're at PyCon, I'm sure I'll be there and I might be able to say hi. Anyways, you can do this tuple unpacking. So you can say XYZ equals LIS3DH dot readXLG. And what this will do is this will create an XYZ variable and assign these 3 values to it, so that you can more easily deal with this in your code. So now I can see what that X value was, what that Y value was, what that Z value is. So really nice. The thing I love about Python is you've got that expressive syntax like this. So nice little Python tip there. Okay, that's how you use the accelerometer. It's that simple. Just call readXLG and you're good to go with this. And you know, you can do fun things like detecting the motion and orientation with that. And then in the guide, let's see. So I mentioned the accelerometer usage here. I mentioned the click detection. So the click detection, this is pretty straightforward and easy to use. So for this, I mentioned there's another function you want to call, this set click function. So let's look at this. So I'm going to call lis3dh.set_click. Now this takes 2 parameters, or at least it takes 2 required parameters, and then there's some optional keyword parameters that you can specify. The first parameter is a number. It's a value either 0, 1, or 2, and this is the number of clicks that you want to detect. So 0 means turn off the click detection, 1 means that you want to detect a single click event, and 2 means you want to detect either a single or double click event. For this. And I don't think there's a way to detect only a double click event, although you'll see when you read the click state, it tells you independently either single click or double click. So if you don't care about single clicks, you can still just look for double clicks. In this case, let's turn on the double click mode. So we'll pass 2 to that. And then you need to pass a threshold value. And so this is kind of like a magic number that just tells the sensor how sensitive the click detection should be. And I believe the higher the number, the less sensitive it is. I might be wrong on this. You might want to look at the data sheet. But I mentioned in here, this depends on the range of the accelerometer. So in the 2G range, a value of like 40 to 80 kind of makes sense for this. And again, you might need to tweak this depending on how sensitive you want the click detection to be. In my case, since I have the 2G range, I'll set this to 80. Now, I do mention in the guide there are some other parameters. You can pass in a time limit, time latency, or time window. Stick with the defaults, but you can adjust these values. You probably want to read the data sheet like I mentioned here to see what those mean. It just changes how sensitive it is for the click detection. Okay, so I'll do that. Now, to get the click detection state, you just call the read click function. And this returns a 2-tuple of Boolean values. So it returns 2 Booleans. And the first Boolean is your single click, true or false. And the second Boolean is your double click, true or false. So if it detected a single click, the first value is going to be true. If it detected a double click, the second value is going to be true. And these can independently be true and false. You might see both of them true or both of them false, like in this case. Now you probably want to call this in a loop so that you're just continually monitoring this. So actually let's import the time module, and then let's do a quick little infinite loop here. So I'm going to say single comma double equals my LIS3DH dot read click. So again, use that tuple unpacking. And then if single, let's have it print out single click. And if double, we'll have it print out double click. And then I'm going to give it a small sleep because I want to give some time back to do any interrupt processing. Usually you don't want to do an infinite loop that doesn't have any sleep inside of it, because sometimes there's interrupt processing and things that happen in the background. So like a little maybe 10 millisecond sleep makes sense to do here. So I'll do that, and then we'll let that run. Okay, so now it's running. And if I tap the board, notice that how it just detected there's a single click, and it's running so quickly that single click, like I said, there's a time window here and a limit where it's detecting these clicks. So that's why you see multiple events. Again, you can tweak those parameters a little bit if you want to adjust this, if it's like more if it's too sensitive or not sensitive enough for you. But if I double click this, you can see it's detecting those double click events. And you do notice it gets a single click event and then it gets a double click event after that, which kind of makes sense. I mean, to detect that click, I have to tap it twice. It is kind of cool. It is sensitive enough that, I can tap the table here and it can detect that. So that's, it's not just the chip itself that you have to tap. And again, you can tweak those thresholds to make this more or less sensitive for you. So that's cool. And I can press Control C to break out of that loop. It actually, Control C on the SAMD21 right now actually resets your board. So just FYI, just reset it. But it's not too hard. I'm going to just go back and reinitialize this. Oops, native IO, and then import the Adafruit LIS3DH module, create that I2C interface, and I need to pass in the clock and the data line. And then the last thing I'll show off real quick is the analog to digital converter. So I'll show how to use that on this board. So let me just make this object first. Oops, LIS3DH I2C. There we go. Okay, so the analog to digital converter. So there are these three little headers right here that I don't even have populated right now. But these let you access, there's an analog to digital converter on this chip. It is a 10-bit, I believe, analog to digital converter. But it's a little bit limited from what I understand. And I mentioned here, you should look at the LIS3DH guide. It has a little more detail about this. But it can only measure voltages in a very small range, between 900 millivolts to like 1.2 volts or 1200 millivolts. So, this isn't as general as the analog to digital converter that's probably on your board already. But it's there if you don't have an ADC and you have some value that's within that small range, you can potentially use it. And it's really simple to use. So on the LIS3DH, there are two functions. There is a read ADC raw function, and you pass in a number, either 1, 2, or 3, and that just reads the A1, the A2, or the A3 channel. So if I pass in 1, that gives me the raw value. And again, read the guide. I link to the main guide for the LIS3DH sensor, which talks a little bit about this. So the ADC, it gives you a value that goes from negative 32,000 to positive 32,000. And so you can see this is giving me a value of 6,000, which, since I don't have anything hooked up, you're just seeing kind of some random noise, basically. If I touch this, then yeah, okay, you see I get some different values because the capacitance of my finger is kind of changing that. But you can see that's the raw value, which might be interesting to you. I also added, as a convenience, a read ADC underscore MV for millivolt function. And so this just does the conversion that the Arduino code does. I think in the example it shows how to do this conversion. So it tries to convert this to a millivolt value so that now you can see this is like 1200 millivolts roughly that it's seeing right now. And if I hold my finger on here, then we get like, okay, there's the maximum 1800 millivolt value, for example. So just handy little thing. Again, a little bit limited because that voltage range is awfully small. You'll have to do, if you had like, I don't know, like a an analog sensor, you know, you'd need to offset its voltage and like squeeze it down to that range. You'd have to do some op-amp magic probably to get it within that range, but it's an option. It's there. It could be useful potentially for you. So, okay, that's it. That's how to use it interactively at the REPL. I guess real fast, I'll just show running one of the examples since I mentioned it in the guide. And let's use the accelerometer example. So in the guide, like I said, there's example code that comes with the library. You might need to download it from GitHub. So there's this excel.py file. And like I said, in the guide, you do need to modify this file and uncomment only one of these three options, depending on how you've wired it to your board. By default, the hardware I2C interface is uncommented, so I don't need to change anything in this example. And so I'm going to go to, this is a directory where I actually cloned this repository locally. You can just download it from GitHub. I'm going to go into that examples folder, and you can see I have the excel.py example in there. I'm going to use the ampy tool to run this code on my board. So I'm going to use ampy. I need to tell it the port for my board, which is this USB modem device. And then I'm going to tell it the run command. And the key thing is give it the -n option to tell it to run the script but not wait for any output, because this script has an infinite loop inside of it. So it's going to run forever just printing out the accelerometer values. So I'm going to do that, and then I need to tell it to run that excel.py script. Okay, so ampy just started the script on the board, and now I'm going to open up the serial terminal for my board. So I'm going to open up that USB modem device, 115200 baud, and now you can see it's just in a loop printing those acceleration values. So you can see like the z-axis sees about 1 g of acceleration in this orientation, but if I flip it around upside down, now it's -1 g. If I hold it in this orientation, now the y-axis is like -1 g of acceleration right here. And then if I hold it in this orientation, now the x-axis is like 1 g of acceleration. But if I flip it around like this, now we get kind of -1 g of acceleration in the x-axis. So that's pretty cool. I mean, you can imagine like putting this in a cube, and then you could tell which side of that cube is facing down just based on which axis sees roughly 1 g of acceleration. Pretty cool. And you could actually do, if you had like a 20-sided dice. I think Phil B has an awesome talking 20-sided dice project. Again, you just have an accelerometer mounted in the center of it, and then based on how you read those axes returning values, how they're in between like 1 and -1 g of acceleration, you can tell how this thing is oriented relative to the ground with Earth, where gravity is pulling it. So that's it. I think that's all I wanted to show in this guide. It's just the basic usage of this module with CircuitPython and how to wire this up to the board and install the library and get started with it. And hopefully this kind of showed off just how easy this is to use with Python and MicroPython and CircuitPython. And again, kind of that advantage here is that you saw with the interactive REPL, I was able to just start interacting with this sensor and reading that acceleration value without any IDE or setup or anything like that. So this is really cool stuff. I'm super happy to start seeing some of this stuff come together and showing off some of the cool stuff that we can do with Python and some of these sensors here. And the whole reason why I've been playing with the LIS3DH is because of this little thing right here. So this is a prototype board of the Circuit Playground. That's Adafruit's kind of all-in-one programming board. So it's got some sensors, it's got some NeoPixels, all kinds of things built into this. But this is a version that uses the same chip as on this Feather M0 right here, the SAMD21 microprocessor. So that means this Circuit Playground can run CircuitPython. And the cool thing is, in the center of this board, actually right here where my finger is pointing, that little, it's hard to see I guess with the light, there you go. That little chip is an LIS3DH accelerometer. So that's pretty cool. We've got a CircuitPython module for this. Pretty soon we'll have a CircuitPython board that has the LIS3DH included in it. So you can imagine there's going to be some cool examples and fun stuff you'll be able to do with Python code on a Circuit Playground running CircuitPython using that accelerometer to detect things like orientation, to detect motion, shaking this, throwing it in the air, dropping it, free fall, that kind of stuff. Lots of cool stuff to look forward to in the future. So hopefully in the near future we'll start getting some of these prototype boards and things into people's hands and playing with some of this in Python. So look forward to that in the future. Let's see. So if folks have questions, throw them into the chat, and we'll jump back to the main view and see if we can answer them. I don't see... Okay, so someone was wondering what's the best board to get started with CircuitPython or MicroPython? Great question. So I would recommend probably the ESP8266 right now, just because you can use either MicroPython or CircuitPython. It has a lot of memory, at least more memory than the M0 boards. It has like 96 kilobytes of RAM, and like the flash memory depends on the module they're using, but usually around like 2 megabytes or so, or megabits of flash memory. So that's just the easiest, and they're inexpensive. It's like $15 for a nice little breakout board. So that's a good one. It gives you a lot of options. You might have one already because the ESP8266 is so popular. The SAMD21 is a good option if you've got the M0 boards. But again, it's less memory, a little less power than the ESP8266 right now, and it only runs CircuitPython, so you can't use the upstream MicroPython with it. So just be aware, some differences there. But in the future, there'll be some fun boards, like I mentioned, the CircuitPython Circuit Playground that uses the M0 board. So, but if you're just getting started today, boy, having trouble speaking. If you're just getting started, the ESP8266 would be my recommendation. Pick one of those boards up, and you can use either board, the M0s or the ESP8266 with Arduino. So if you get bored with MicroPython and CircuitPython, you can go back and use Arduino code and do things the Arduino way with those boards. So it's you're not limited to just CircuitPython and MicroPython with these boards. So that's what I recommend. Let's see, and I think that was it as far as all the questions go. So that's it. I'll wrap up this video. So thanks a lot for watching. This was Tony from Adafruit, and I was showing off how to use the LIS3DH accelerometer with CircuitPython. If you like this video, then check out youtube.com/Adafruit. That's where I have this video and all kinds of other fun videos there. Lots of projects, pretty much a video every day almost, I think, is published there. So check that out. Check out twitch.tv/Adafruit. That's where I stream these projects and videos live. So if you want to watch and see how things go, so far so good. Haven't had any major disasters yet live. Knock on wood, I guess, that it continues like that. So if you like to watch things, check out twitch.tv/Adafruit. There's all kinds of live broadcasts and things that we're doing these days. And otherwise, if you like this, click the like, the comment, the subscribe button. Let us know that this is good stuff, and we'll keep making content like this. Oh, and by the way, too, if you like this, I usually stream things every Friday, so that's kind of the day that I do things. So check out Twitch on Fridays, and you'll probably see a new stream like this one. So until next time, this is Tony from Adafruit. So thanks a lot for watching. See you later.